All right, so we're gonna go ahead and move on. You guys have about a minute to put what you think radioactive decay means. Right, 5, 4, 3, 2, and 1.
Of radioactive decay, but they all have similar patterns and similar characteristics. Our next word is isotope. An isotope is two or more atoms that have the same number of protons, but a different number of neutrons. Because they have the same number of protons, they are the same type of element, but because of the different number of neutrons, they have a different atomic mass. For example, we might have carbon 12, carbon 13, and carbon 14. Each of these isotopes of carbon has the same number of protons, which is 6, but a different number of neutrons, which is 6, 7, and 8, respectively. Next is a parent atom. A parent atom is the atom before it undergoes radioactive decay, which is followed by a daughter atom. A daughter atom is the atom after it has already undergone radioactive decay. Our final important term is a half-life, which is the amount of time it takes for half of the parent atoms to decay into daughter atoms. Now, every radioactive isotope has a specific half-life. For example, carbon-14 has a half-life of about 5,730 years, while uranium-235 has a half-life of about 7.
Right, so what is a half-life? In grad school, we worked with P32, and I think its half-life was around 28 days. I might be wrong because it's been 25 years since I've thought about this, but we would take our radioactive X-ray material when we were done with an experiment, put it in a drawer and shut it, and pull it back out in a month, because then it would not be radioactive anymore. So knowing that half-life helps us use some of these things in science all the time. So what is half-life? Good, Jenna. All right, one more minute. All right, 30 seconds. Five, 4, 3, 2, 1, go.
About 704 million years. From these examples, we can see that the length of time of a half-life between elements can vary greatly, and it is dependent upon the specific isotope. Let's look a little more at this term half-life. We can understand it better if we look at a graph. On the vertical axis, we have the percentage of parent atoms remaining in that rock sample from 100% down to 0%. On the horizontal axis, we have the number of half-lives. If we look again at the definition of half-life, which is the amount of time it takes for half of the parents to decay into daughters, we can see that each half-life reduces the percentage of parents in that rock sample. If we look at this closely, we can see that at 0 half-lives, or at the moment of formation of that rock, we would have 100% of the parent atoms. At 1 half-life, half of those parent atoms would have decayed into daughters. So our percentage of parent atoms would be 50%. After another half-life, or on the second half-life, that 50% of parent atoms would have decreased by half. So it would now be 25% of the original parent atoms. And all
right, we're going to be taking our data today, and then on your own tomorrow, you'll be graphing something like this. So you're going to do your half-life and your proportion of parent atoms remaining and graph it out. You're also going to be doing putting in an actual time in seconds that will be different for everyone. Good. Okay. 5, 4, 3, 2. Yes, those are spoilers, Kate. Do not look at the chat box when you're doing your own. All right, we're moving on. That should only take a second to click.
All the rest have turned into daughter atoms. If we continue this pattern of half of the parent atoms decaying into daughter atoms every half-life, we can see that, like we said, there are 50% of the parent atoms remaining after one half-life. After 2 half-lives, there are 25% of the parent atoms remaining. After 3 half-lives, there are 12.5% of the remaining parent atoms. After 4 half-lives, there are 6.25% of the parent atoms. So in the simplest form of radioactive decay, the percentage of parent atoms compared to the percentage of daughter atoms helps us to determine the number of half-lives that have elapsed. Keep in mind that radioactive decay is a spontaneous event. We cannot look at a single radioactive element and predict exactly when it will decay. But when we look at a large number of elements, it becomes a predictable pattern. Let's compare this to what cited is probably the most common everyday random or spontaneous event. This is a coin flip. It's true that with any single coin flip, it's impossible to predict whether it'll be heads or tails. However, if we look at hundreds of thousands or even millions of coin flips, it becomes a very predictable pattern. The results will be very close to 50% heads and 50% tails. This is very similar to what happens in radioactive decay. Just like the coin flip, we cannot predict exactly when any singular atom will decay, but as we look at a large number of them, it becomes a predictable pattern, this pattern of half-lives.
All right, how is a coin flip or Skittles or M&Ms, whichever thing you are going to use today, similar to an atom's radioactive decay? So why do we use these things to simulate radioactive decay? So put your best guess. Why do we have you, we're going to have you today using coins, Skittles, or M&Ms, shaking them up, and then looking at how many of them turn over and have one side or the other up. And then we're going to say that that number has just changed into a more stable state and emitted some sort of particle of energy and matter. Yes, you could. Well, beans won't work. Beans are good for representing the daughters that become stable, but you'll need something that's unstable that has 2 sides to be your parent atoms. But what we're going to do is I'm going to have you guys go into pretty big groups. That way, at least hopefully some of you will be able to be doing the activity and sharing data with your group if you ate your Skittles or your M&Ms, like Selena. All right, 30 seconds, or you're penny. No, hopefully no eating of pennies. All right, let's do it.
Where half of the parents decay into daughters every half-life. And as was stated earlier, each radioactive isotope has its own unique half-life, or the amount of time it takes for half of the parents to decay into daughters. Let's look more closely at how this relates to rocks. When we're talking about radioactive decay, in nearly all situations, we're talking about igneous rock. This is because when an igneous rock cools or forms from magma or lava, the radioactive clock starts from 0. What is meant by this is, in the simplest form, there are 100% parent atoms and 0% daughter atoms. This makes it a reliable clock for us to monitor the ratio between the parent atoms and the daughter atoms and use this to determine the age of the rock. And once that igneous rock solidifies, the parent atoms begin to spontaneously decay into daughter atoms. We use these properties of igneous rocks to analyze the percentage of parent atoms compared to daughter atoms. Again, in its simplest form, we look at that percentage or that ratio to parents to daughters to determine how many half-lives have elapsed. And then we can use how long the half-life of that specific isotope is to determine the age of that rock. Let's say, for example, we have a rock sample that contains a ratio of 12.5% of the parent atom, uranium-235, and 87.5% of the daughter atom, which is lead. Using this ratio of parent atoms to daughter atoms, we can determine how many half-lives have elapsed since this rock was first formed. If we look back at our graph, we can see that a sample that contains 12.
Right. So the questions that go with your lab today will have you work backwards like this, because this is the important part of this, is how can you figure out the ages of different things using these radioactive isotopes and these half-lives. So once you plot your graph, you're going to be working backwards to figure this out. The one thing that was confusing to first period, and it's always confusing to students, is I want you to time yourself and go through 10 of these, even if you get down to zeros over and over again. Okay, so we're going to go through 10 half-lives of shaking, and you're going to time it. So at the start, and then once you told everybody in your group that you're done with your 10, you stop your time, and then divide by 10. So everybody ends up with slightly different number of seconds, and that's okay. But that's what we're going to be putting down here underneath our half-lives, exactly like the number of seconds it took for all of your Skittles or M&Ms to disappear and change into a more stable state.
0.5% of the parent atom has undergone 3 half-lives. Our next step is to multiply the number of half-lives by how long a half-life is for uranium-235. Now, if we multiply the number of half-lives, which is 3 in the case of this sample, by the length of a half-life for uranium-235, which is 704 million years, we can determine that this rock is over 2 billion years old. Now, this is a very simple example of how absolute or radiometric rock dating is used to determine the age of rocks. But it applies to the general principles and the general processes that are used to determine the age of rocks, fossils, and other items. Radioactive.
All right, and I did get an email and then went and checked on your Google form quiz that's due Sunday. There is a typo on the one question about radioactivity. The second number that says something about 10 to the negative 5th is actually supposed to be 10 to the negative 7th. So you're working it correctly, or you should notice that there isn't a right answer unless you change that second daughter atom's value to 10 to the negative 7th curies. So just note that there is one typo on your Google form quiz. All right, we are going to return now to your stream page and go physically, kinesthetically do this activity. So go to classwork, go to this week, and then you're going to click where it says, I'm on the wrong week, half-life of candium, and then open half-life of candium radioactive dating. It will allow you to make or it'll prompt you to make a copy for yourself. And what we're going to do is I'm going to be putting you into groups. And when you get into your groups, whoever has a pet that is in their house, whoever has the most number of pets goes first, and then the next person and reads the discussion, then the next person with the next number is reading background information, and then read your procedure. Okay, and then you are going to start shaking all of your atoms and filling this out. I am going to be jumping in and out of rooms to hear you reading and then to answer any questions. It takes about 5 minutes to get through usually 10 half-lives. Bread does not count as a pet or a dragon because you don't have a dragon. Okay, I guess you can maybe count your little brother. All right, are we ready to read in big groups? Make sure that if you have your pennies and your Skittles or M&Ms, whatever nearby. We're going to be in fairly large groups so that there's, before we get into groups, sorry, I need you to write, yes, you have your supplies. So put a green check mark by your name. I need to see how many of you have your Skittles, M&Ms, or pennies and something to shake them in. That way, every group has several people that have data that they're going to share while they do it. I see 1, 2, 3, 4, 5, 6, 7, 8 of you. 9, okay, good. Looks like there's quite a few of you. Good. So let's do this. I'm gonna open your breakout rooms, and then I will be jumping into them to answer questions and to listen to you reading the discussion background and then the procedure. Okay. All right. Your room should be open.